Educated session, and hear from the booming goals, and we try to hit them. So that's what this is about. So there's going to be 3 certificates available: a wide field, solar after start the session, and hear from the booming issues to how you find out the problem, we try to hit them. So how you feel about the image, maybe what happened that night. Here's an example of the application form. That's what this is about. So there's going to be a session, and hear from the booming issues to how you find out the problem, you try to hit them. How you feel about the image, maybe what happened that night. Send it internationally. Here's an example of the application form. That's what this is about. So there's going to be a session, and hear from the booming issues to how you find out the problem, you try to hit them. How you feel about the image, maybe what happened that night. Send it internationally. Here's an example of the application form. That's what this is about. So there's going to be a session, and hear from the booming issues to how you find out the problem, you try to hit them. How you feel about the image, maybe what happened that night. Send it internationally. Here's an example of the application form. That's what this is about. So there's going to be a session, and hear from the booming issues to how you find out the problem, you try to hit them. How you feel about the image, maybe what happened that night. Send it internationally. Here's an example of the application form. That's what this is about. So there's going to be a session, and hear from the booming issues to how you find out the problem, you try to hit them. How you feel about the image, maybe what happened that night. Send it internationally. Here's an example of the application form. That's what this is about. So there's going to be a session, and hear from the booming issues to how you find out the problem, you try to hit them. How you feel about the image, maybe what happened that night. Send it internationally. Here's an example of the application form. That's what this is about. So there's going to be a session, and hear Today's talk, I'm doing meters, but the next time I do one of these sessions, I'll do one on the side because I've been a little bit successful with the hydrogen alpha scope, and we're going to have the hydrogen alpha scope available. Today's talk, I'm doing meters, but the next time I do one of these sessions, I'll do one on the side because I've been a little bit successful with the hydrogen alpha scope, and we're going to have the hydrogen alpha scope available. Today's talk, I'm doing meters, but the next time I do one of these sessions, I'll do one on the side because I've been a little bit successful with the hydrogen alpha scope, and we're going to have the hydrogen alpha scope available. Today's talk, I'm doing meters, but the next time I do one of these sessions, I'll do one on the side because I've been a little bit successful with the hydrogen alpha scope, and we're going to have the hydrogen alpha scope available. Today's talk, I'm doing meters, but the next time I do one of these sessions, I'll do one on the side because I've been a little bit successful with the hydrogen alpha scope, and we're going to have the hydrogen alpha scope available. Today's talk, I'm doing meters, but the next time I do one of these sessions, I'll do one on the side because I've been a little bit successful with the hydrogen alpha scope, and we're going to have the hydrogen alpha scope available. Today's talk, I'm doing meters, but the next time I do one of these sessions, I'll do one on the side because I've been a little bit successful with the hydrogen alpha scope, and we're going to have the hydrogen alpha scope available. Today's talk, I'm doing meters, but the next time I do one of these sessions, I'll do one on the side because I've been a little bit successful with the capture, the bigger the object that you can catch, and the larger the aperture, the faster you can catch that light. So when you're doing it, you know, and you want to get bigger apertures, you can get longer focal lengths. And one of the problems with this is now you have a longer focal length, you get a smaller area of sky. But if you're trying to capture a meteor from a shower, you know they're all over the place. So now if you're shooting in one area, what's the odds of you just capturing in that area? So there's got to be some sort of balance. What's the best way to capture this and balance with actually getting objects, not having too tight of an area that you're shooting in? So here's a chart that's got 5 different lenses here, and generally the focal ratio, the fast focal ratio of most of them. And then, so here's the diameter of the lens, how much light you're letting in, the square area of millimeters of light that you're letting in. So that part's really good. You know, talking about how you get longer focal lengths, you get more aperture. But the problem is, then you get a longer focal length, and that point of light shoots across the frame of your field faster. So it actually doesn't stay in any one spot longer, and it's actually harder to capture. So there's got to be a balance there somewhere. What's the good lens to use and capture, you know, reasonably bright meteorites? So they did the analysis, and here's the relative exposure. And basically it's saying that with a 50 millimeter lens, that's probably your best chance relative to capture meteors, as opposed to a 60 millimeter, where you probably get about a 12th of it. And then you can shoot with a 135, but that's with such a small field, you know, you're likely to get one in a frame of field. So to capture meteorite, probably the best lens normally to use is a 50 millimeter lens. And when's the best time to shoot it? Well, obviously when you know that they're flying. On a normal cycle, the number of meteorites, the meteors that you can see is usually maybe 5 ZHR, which is the number here, the number per hour. You can see the whole sky at one time, 5 in an hour. Now, if you're shooting in an area, what's the chances to be in that area? So you want to shoot during one of the major showers where you know right off the hop that there's more per hour. And when I shot these shots, I was shooting there where they say it's 50 to 100. So what you want to really do, if you want to shoot meteorites, you shoot during the major showers. And that's the 3 of them. And I'm very disappointed to point out that the Geminis, which is probably the best shower this year, occurs, I think, a day before the new moon. Yeah. Sorry. But best time to do is, you know, during the showers. And the best place to shoot, to capture them, is probably about 30 to 45 degrees away from the radiant. So you can get the radiant in it. But shooting in that area is probably the best place to capture them. But I wanted to do something a little different. I had seen images that somebody else had done. Bill Crosby of our group had sent with an image, and he had one of these composites. And I thought, I want to do that. So in order to do that, I sacrificed not using a 50 mil with a smaller field. I'm using a camera lens that was much wider, so I could catch a wider area, but I knew I was going to sacrifice getting fainter meteorites. So I know I'm getting less meteors, but I'm getting, you know, a larger area. And I am shooting during the showers, so I'm hoping that'll work. One more thing I wanted to point out is, as a member of the RASC, you're getting Sky News magazine. And just recently, they kind of got on this imaging kick as well. So in the last 2 issues, there's major articles in them about how to get started. Really beginner, right down to the, you know, simplified facts of how to get started to do imaging. And I would suggest, rather than me trying to explain it here tonight, you get into those articles. And you take a look at Sky News. Getting started in astrophotography. Nicely well done article. And I want to point one thing out here. See this device here, this hand? I'll talk about that in the next frame. Okay, so what equipment did I use to shoot this? Well, I used the DSLR with I used a zoom lens, but I know it's a zoom lens which is an excellent zoom lens. A lot of zoom lenses are very poor, but this is a zoom lens that is known to be, you know, very good images wide open. So between 11 to 16, photographers who do just regular stuff say it's an excellent lens. So I'm using that kind of lens. And the nice thing about that lens is when it's at 11 millimeter zoom, and I take it down, by the way. I set it to 11, and I take it down so it won't adjust change. And then I move the focus right to infinity, and that lens is in focus, which is nice, because I don't have to go through the whole process of trying to focus. I know it's in focus. So it's a beautiful lens for that. The device I was pointing out earlier is an intervalometer, and that's a device that's used to set off your camera. You have a plug on the side of your camera, and you can plug in, and that thing will trigger it and run exposures on a regular basis. And those exposures will be, whatever time frame you program into that intervalometer. You could say, I want 30-second exposures, and I want them 2 seconds in between every exposure, so it gives the camera time to download the image. So shoot at 32 seconds, 32 seconds. And if you set it up right, it will run all night for you. Okay. When I shot my images, I did shoot it on I have one of these sky trackers. There's this iOphone sky tracker. There's a number of different ones. And what that does is it guides all night. So literally, when I'm shooting for 6 hours, at the end, basically, the center of the frame that I have is the same as when I started. So it makes it easier to match them up. One more thing I wanted to point out here, I didn't talk about this, remote powering. You're going to be running your camera all night, especially if you're going to be trying to get the gem heads or some of the other showers. The batteries will die very, very quickly. So what you would like to do is have it, you can get these power pack units that plug in, and they run off either 12 volts or 110 volts, and they allow your camera to run with power without draining any batteries or anything. So I have remote powering, and I have the sky tracker, and that requires powering. So that means I carry around with me a 12 volt battery pack that powers these things up. And then, of course, on top of all of this, right at the bottom here, you don't see, but using this to be tripod, something that the won't wave or won't shake in wind. So you set the camera to JPEG. That's what I would suggest, the largest to get the most detail out of the frame, not RAW, but JPEG. Set it to manual, bulb mode, and then you start. My suggestion is start with one frame where you've got the camera sort of stopped down, which helps improve your image, and then you use a lower ISO so that gets rid of the noise, so you get a nice background frame, and we'll paste everything on this nice frame. Then we open up the ISO, we put it to the highest speed. In my case, it's 1600 in my camera. Set the lens wide open at f2.8, so I'm driving as faint as I can, and then run exposures of 30 to 60 seconds. If you're not using a tracker, use the 500 rule. 500 divided by the focal length, 11, is about 40 seconds, but 30 seconds is probably what I would suggest is the maximum if you're just using the tripod. And then shoot for 3 to 6 hours somewhere near the peak. If you're not tracking, this is what happens. The lightest area in the middle is the only common area. That's full frame on the outside. So if you have then one, you've got meters that are here, well, you can't put them into to guarantee that they'll be in. So tracking allows you to have a full frame and put all of it into it. Processing. So now you've shot, and at the end of the night, you've got 300, 400, 500 images, and you go to sleep because who wants to look at them that night? But the next thing you get up, you take a look at them, and you look and find which ones are there. Take those frames that have meters, write down the number, and write them down, put them into a separate folder. Always use a separate folder for your images. Don't use the base image, save your originals, and use a separate folder. Now in the processing that, go ahead.
Thanks, Dan.
Well done. I know he could come out of town, so. So when I looked at my images, I had some aurora the night that was done, and there's a little bit of the sky pollution because I was shooting in town too long that's darker, but still had some. So I wanted to use a program called Iris, which is here's the keyword, free imaging processing, and then I combine all the meters in a package, a Photoshop CS2, which also I have a free version of that I use. So there's what IRIS looks like. Just type in IRIS, astronomy, and it'll come up with this AstroSurf, and you can download the program from there. So there's the difference. What I do is I have it do a gradient, and it takes a look at the background sky, and it finds all that yellow stuff and the ugly stuff, and using that program, it will remove it. And you can see how the bottom thing is much more pleasing than with the blue. So it helps you basically remove the yellow from the light pollution. So here's the program. You go with the file, and you open up one of your images. And there's the image I opened. And again, this is one of the originals. You can see it's kind of got that brownish background to it. So the first time you go under processing into that the camera processing up here, go under that, and under its options is wavelength. So you select wavelength. You go into this box, set these first four to 0, leave this one at 1. And set OK. You only do this once, and what it will do is, there, it creates an image of the background, sort of, it's sort of like softens it up. So it's not picking on a thicker spot, it takes a larger sort of softening. Then you go and open up the command window, the box there, and you start typing in commands. So on this image that you had, you save this blurred. And this is the file name that I selected for it, and then hit return. Then you load the blurred into there and hit return again. And now these are commands that they have to do this. So these are the commands you will simply use when you go online. It tells you the commands are, and we can get these to you in the newsletter if you like, with the different the steps are here. Then you type in subscribe, sin, and then save sky grade return. So the result is what I've got in the background there. That is like the pollution that's there. I've got now a frame that says this is the noise that's, and the color of the noise that's in the background. And then you type in the command sub, which means subtract the subgradient, 100% of it, visual 180/50. I'm not even going to get into what that is, but that's what the commands you use, and bang, there's the image. You notice how now it's blue. The pollution literally has been removed. So this is kind of a nice thing. And you do this for all of the images that have the meters. So with the meters in. So you kind of clean up the sky in all of them. The nice thing about that other program is you can use it for other things, except your aurora images if you want to get rid of that. But if you've got other sky images, you've got light pollution, and you want to try to save them, you can use that program for it. Now to combine the images, I use Photoshop CS2. And it's a nice imaging program. And the final is, to follow it along, you could also go to Dave Kingham, type Kingham and meteors and Google on that. It'll come up with YouTube, and he'll show you exactly what I'm doing. So that, you know, if you don't catch this here today, you'll catch it there. So if your images were tracked, then it's easy. They're all the same, and we can miss one step. But if they're not, then you just use a tripod. Then what you're going to have to do is actually physically move each image to sort of match up to the background frame. Then we're going to use the brush tool, which is one of the tools in it, and we're going to paint the meter right into the image. So here I go, file open. P1A was my first image cleaned up. I just gave it a new name, P1A. So I open that. There it is. Then I go and I click on the picture itself, and with the left click, and it comes up with this thing and asks what you want, and then choose duplicate file. So I create a duplicate background for it. So in Photoshop, on one side, there's the layers. Photoshop does things as layers, you know, different layers like this. So what we've done is we're going to use the background as the bottom, as the base. Or use the original as the base image, and we'll put new layers on top. Then we go into this layers palette here. That's the one on the side. We go down to here and we create a new layer. And you'll see that in the next frame. And then we open that, then we open up a new file. Okay. This is where the layers is, and this is where we're going to create the background and then the new frame. When we open up the second frame, it opens it up as a totally separate frame. So we've got the background over here, it opens up the second one as a totally different frame. So we said, here's the image 2, we want to top image 1. We go into the select menu at the top and select all. So what we're going to do is say, I've got other image, we just take it and select the whole thing. And make a copy of it, go into edit, copy. And then we'll go back to the first image. And go here, where it says layers 1 right there. We're going to paste it into there. So when we paste it, we literally say, I'm going to take this image and I'm going to slide it from this to the top of this one as a new layer. I go up here. There's normal, there's a lighten, which will allow you to see all the light of all the images. Change the opacity to 50%, and that means it's sharing light from both images and where they are. So the first meter is over here, the second one is over here. So, now, if you have to move the images, we're going to use a function. I'm just going to basically touch on it here, called image free transform. So basically, when you have the two images run on top of each other, you can see both. You're going to have to shift one to coincide with the matching stars of the other. And here's a prime example. So you'll open up the second frame and you'll say, oh, look, these stars are not lying. There's the same star there, it's not lying. So you'll literally take this and shift this around until that star is on top of that one's on top of that one. If you need to twist it, you can do that. And then there you are. You've got the 2 meters. This is the original, the first frame I had. Here's the second one. And I take a little post-it note and put it right on top of the screen of my computer to remember exactly where it is, knowing it's right there. In Photoshop, on the left-hand side, there's a whole menu of things here. So, before I get into that. So, I will go back to the original image, the new layer that I pasted in, and I'm going to do a function called reverse layer mask. So it's done by actually going on here and alt-clicking on this one button that's at the bottom. This should be here. So at the bottom is a frame that says create mask, and you shift on it, I'll click onto it, and it'll take that layer and I'll kind of hide it. So all of a sudden you'll just see the background of it. Then I go to the left-hand side tools and I'll select a brush. I'll click on the down here, this is called the foreground layer. I'll click on here, to shift these two around so the white is there. So now the white, the brush will use the white as a paint. And this is where the magic happens. So I'll go over here, and as you bring the brush onto the original photograph, it has this circle. And as you bring the circle into the area where that line was, it will slowly, when you click it out, it will reveal the meter right there. So literally, you kind of paint over it as if you're removing a layer of something, and that meter shows. You can go back to that foreground thing that I showed you earlier, so I changed the way, and change it to black, and that will allow you to go and correct. If you have a meter that's right beside a bright star, and that bright star comes up when you grab it with this tool, you may have to remove something. But normally you make this little tool very small and just go right where you need it. Just gently back and forth over that spot. And that's how you capture the second one. It's really a neat process. And then after you've done, say, a hash to 5, I would suggest, save it. Because if you do some things and you mess one up, you kind of got to go to the back to start again. So if you do have to go every 5, you can save it. When you do that, you're going to the main menu, under the layer function, flat. And you just, each meter image that I had, I went and did that process. I just went there. The only thing I don't like about this one is this one had a little bit more noise that kind of shows up there. just kind of on the outside of that. I couldn't really get rid of that noise. But all these others are just basically all meteors that were in the frames, all just combined and put together into one frame. So that's how I came up with this. And what I'm thinking is I'll just write a little bit about this, and I'll put this inside or hassle of the maintenance, which could maybe put it in the next week's list. But that's basically what I came up with. So maybe for a couple of minutes, is there any questions on that? Yes.
JPEG rather than RAW.
RAW's take too long to download, and it's way more than you need for this.
In my case, there was just no way.
A large JPEG actually is a pretty decent file. And you know, we shoot RAW when we're shooting objects where we're going to do a lot of other functionality to it, like flat frames and dark frames against them and such. That's where the RAW works better. But these, I don't think you need it. Question? You want to do one?
In your last image,
Yes.
you want to describe for the new people what you're seeing here. You've got one sporadic gradient, and there's some stuff up in the upper right that doesn't seem to be associated.
And that's true. So here's about where all these are radiating from. Right? These are not draw a line through them. All these, this one, this one, this one, this one. Then you go, what the heck is this? That's what Jay's talking about. That's a sporadic. That's like the 1 in 5 during the night. And that just happens to be a very bright sporadic. All these are all Perseids. This is from a different shower. This one up here, by the way, this is also a Perseid. And I'm going to ask, what's that shower called? The delta aquarius, okay. So this is a totally different meteor shower, and I just happen to be catching some of them from there. So, do you like this process of going through the 4 steps? You don't care. Is anybody going to actually try to do some imaging? None of them. Okay. All right. So that was it. And one other thing I want to say is that it's amazing how, in this grand universe of ours, how small things and big things do the same thing. Atoms rotate, you know, galaxies rotate. It's amazing. Hurricanes look like galaxies. Well, does this dot look like a recently visited comet?
Yes.
Comet 367. That's my model of it.
That's potato. I think you should send that in as kind of help. Natural water.
Put the Philly leather on it, though.
Right there.
Yeah.
It's in the dirty zone. Thank you.
Oh, you're gonna have.
Okay. For those of you who haven't been here before, my name is Jay Anderson. I'm president of the Winnipeg Center for the next few months. And we'll go into some details about that tonight. We have I think, a fairly interesting night tonight. I've listened to our main speaker at a colloquium this afternoon, and I think he's really going to show us something that is very, very interesting in astronomy. Chris, can you, where's my light switch here? There. So, at the moment then, we had Stan talking about beginning astrophotography, and I'm going to do the announcement, the business part of the meeting, and then we have Brian Tack coming up to tell us what's coming up in the next month in the sky that you might want to be looking at. And Jennifer, who isn't here yet, oh yes she is, and will tell us about what's new. And we all know that Jennifer moved down to Toronto after the last meeting, but she's come back to rescue her cat, so she agreed that she would like to come and do what's new again. And we also have a pile of 13 books or book in the front here, and Chris has a big pile of 13 tickets, double, and we'll be passing them out. And then, as is the process we followed in the last 2 meetings, you can come and lay a ticket out for whatever of these books you'd like to have. You can put all 13 on one book, or you can spread them out across all 13 books and so on and so forth, and then we'll have a draw for them. And that comes courtesy of Ian Cameron, who is desperately trying to clean up his library before he retires away from the university in that process. And I anticipate, if I'm not mistaken, that we will have these kind of book giveaways for a few more meetings after this one. We might have to work out a more efficient way of doing this. I'm not going to give you a lot of time to decide what books you want, but we will do the draw either before the break or probably during the break. So what's our news? Well, the RASC handbook, the 2017 handbook, is just about ready to be shipped to you. For those of you who are not familiar with the RASC, the handbook is a part of your membership in the RASC. This year it's 359 pages long, and so lots of reading. I suggest that it could be in 2 places in your house. It could be beside your telescope or beside your toilet. Both are good places for reading. The toilet, I find, is better for the more in-depth part of it. The telescope, you're usually just looking for the things that are up in the sky that night. Next year, the RASC General Assembly, which is the main meeting of the Society as a whole, will take place in Ottawa during the Canada Day long weekend. Coincidentally, or not coincidentally, it's also the 150th anniversary of this country. The idea is that this will be a pretty good place to hold the General Assembly and catch ceremonies in Ottawa at the time. Now you can get the details online at the national website, rasc.ca, but I thought I would show you a little bit from the menu about what's going on. It starts on June the 30th. And you can see here that there's some business stuff, the National Council meeting. We elect 2 members from the Winnipeg Centre to be our representatives at the national meeting, and most of their travel to Ottawa will be funded. I say that because there will be elections for those councillors later on in January. The idea is they will represent our interest in the National Council meeting. So while everybody else is listening to Ken Hewitt-White, who is a very well-known amateur astronomer who writes columns in Astronomy Magazine and the Sky News, or maybe the Sky Telescope, while the rest of us are listening to Ken Hewitt-White, the national rep will be in a business meeting. So it's the winners and losers on that one. And you can see there's a number of other subjects there. Followed up in the evening by a barbecue on campus. For those of you who are old enough to remember what the Deacon Bunker is, well, you can have a tour of the Deacon Bunker. For those of you who don't know what the Deacon Bunker is, it's a big hole in the ground that the Department of National Defense put together in the Deaconbaker years to hide in. All of the important people in the country could hide in it if we had a nuclear war. On the Saturday, July 1st, there's a meteor workshop. Don't ask me what, but it'll probably cover over details of finding meteors when they're on the ground. Then it is photographing them like Stan showed us today. And then Simon Hammer, the geologist, will talk about, he's done some work on the planet in geology, so he's going to be one of the main speakers. We have several others there. Charles Ennis, who's actually going to be in Winnipeg at the end of this month. And he's looking for one of the members to show him the observatory, and I'd like to volunteer for that. Then, of course, Canada Day celebrations in the evening. On the Sunday, the annual general meeting, that's for everybody, not just the council. And that's where important things are discussed. Although with the new rules that the Harper government put into societies and the way we have to do our own governance, the importance of the general meeting is somewhat declined. They can only advise the executive on things they would like to do. They cannot vote on tell it. And there are a couple of talks, but the subjects have yet to be announced. Discussion of next year's solar eclipse, which is going to become more and more important to it. And finally, the banquet at the end. For those who want to stay until July 3rd, you can go with a tour of all four craters. So it's a pretty full, it's sort of typical of most General Assembly meetings, with the exception that there's probably going to be quite a bit of activity in Ottawa centered around the 150th anniversary of Canada. The new book, Explore the Universe Guide, is in the final stages of preparation and printing, and should be almost ready to go. Should come out anytime to the RASC store, so you can order that online. Designed for starting astronomers. It's been a project that's been worked on for 3 or 4 more years up till now. So basically, for those of you who are interested in getting started in astronomy or getting a little deeper into astronomy, this is a RASC-generated guidebook to help you along the way. Winnicentrics is our local newsletter, and I'm in need of a new editor. We've had yeoman service over the last few years on that project, and you all get a copy of Winnicentrics every month, and so you know what's involved in the work for it. So I have a volunteer who wants to take on that job, and I would be certainly happy to entertain your candidacy. And I'd like to thank Megan very much. There's Megan. There she is for her work that she's done. Elections. Chris, did anybody talk to you about elections? No. So nobody wants to be councillor, nobody wants to be president, vice president, because they asked you last month if you're already on our managing council, you should let Chris know whether you would like to continue in the position or not. You can see from my notes up here that all of the positions that are currently have an incumbent are eligible to stand for second term. But of course, that doesn't mean we can't have new candidates come into the position. And the only position I know for sure that will be open is that of president. Each time you get somebody younger that needs to do this. And we have some people who've expressed their interest in that, but if you think you would like to stand for some of those positions. Now, the national representatives, Kenneth, I think you have decided not to continue.
I can if you want.
Anyway, please let Chris know so that we can plan this election a little better than we have in the past, where you sort of get asked the day of the meeting whether you'd like to stand for positions. And mostly this council does a, it looks after the affairs of the center. It decides what kind of projects we might want to spend money on, what kind of events we want to conduct with the public, basic policy on running the observatory, loaning telescopes, and so on and so forth. So it's actually quite a nice body to have as president, to have people who can help me out. In general, if you're going to be president, your primary job is finding speakers for each monthly meeting. And I would venture to say right now that I probably have speakers lined up that'll take us into February. So we'll get you started. It's not that difficult to do, and there's lots of help from past presidents and members of the council. And if you're really authoritarian, you can appoint somebody on council to look after getting speakers for the meeting. But you find councilors won't want to be too willing. We also have elected or appointed positions, rather, observatory director, webmaster, scope coordinator, Winnicentric publisher, which we now know we need to do. The people who are in those positions should just indicate to Chris, once again, that they're interested in continuing. Council is the one that they would report to. The monthly open house at the UN Observatory, open house at the Telescope on campus in the university have now started up. There's been one in September, there'll be one at the end of October, specifically the 26th. So if you'd like to see the university planetarium, is Danielle here? Danielle, do you want to say something about what you guys planned for these meetings?
Sure. We'll have the same format as here we've had historically. So there will be a 20-minute talk about what's up tonight, starting on the planetarium show, and about a 20-minute talk about what's new. So using astronomy is similar to this format here. It'll be presented by volunteers and grad students. It's a good way to hear about what some grad students in the astronomy department here are doing. And then, weather permitting, we'll open up the scopes on the university. Quite a bit. And everybody's welcome.
Thanks, Danielle. I'll give you a good opportunity to have a look through a 16-inch telescope if there's something up in the sky and clear out. But certainly, because it starts at sunset, it can get pretty early in the evening.
Well, so I teach until 5:30 on Wednesdays, so so it's impossible to start right at sunset. So for the later months, we'll always start at 6:30.
Anyway, keep an eye on that on the university web pages. Give you a little extra dose of astronomy in the middle of the blank space between these meetings. The members observing tonight, Brian, are we going ahead with that tomorrow if the weather cooperates?
Did we?
Full moon, you can look at the moon. Every month. So, well, I shouldn't say the only one because the university's observatory isn't beside it. But anyway, typically, full moons are not a good night to go looking at stars because full moons are they kind of wash out everything in the sky. Anybody went out to look at the alleged aurora last night, they would have found that out. So the clouds we don't. We do loan telescopes out, and Stan is the man to see about that. You've already met Stan.
Oh, okay.
So we have, are these loaners here, Stan? No? Okay. We'll let you take those.
Oh, gosh.
It's a little better quality than ours. Anyway, it comes with some simple instructions, so if you want to take one home for a month and look at the moon and planets and whatever else you can find, we do that. And you just have to make the booking with Stan. You can keep it for longer than a month if nobody else wants it. I think they're fairly popular right now.
There's only one that somebody's already spoken for it, so there's no scope available this month.
There you go. And he was also signaling to me that there are still calendars for sale. There it is. We have the RASC calendar that's produced each year by National. $12. 12 bucks?
12 bucks. Two of the images are from Winnipeg Center Motors.
We sell them at cost, so $1 a month. I don't think you can buy one pack at most for $12. What do they cost these days? The observatory, which picture I showed you, is open to all of you if you are a member of the center, and you can get a key from Brian. That key also opens the worm room, so if you want to go and observe with your own telescope, you have a warm place to get into. with kettle, water, microwave, and even a small computer in it. They finally observatory is about 15 kilometers south of the city. Not very dark, but dark enough.
Once you're on, it's still really okay.
So there it is for announcements. Anybody else got anything they'd like me to bring up? Brian, you will now. Let us know what's going on. You bring your own, or you guys Maybe I should let Jennifer start first. Are you ready to go? Jennifer's ready to go.
I don't know, do I have time to play this movie? It's going to be a couple minutes, but maybe next time. All right, so during the day, what I've done here is around 4 o'clock in the afternoon. You can pretty see that the planets are pretty low in the sky. Much is going to be visible during the day, but what I've done differently is Venus. I've seen Venus during the day. You can't see Venus, and it's probably better to see Venus during the day because the atmosphere is more stable. And how does Venus look like? Well, it pretty much looks like the phases of the moon. But I was told by the handbook that you can view some of these planets during the day, so maybe tomorrow, if it's clear enough, maybe I'll check out Saturn and see how well that's going to turn out. And if you noticed before, we have Mercury and Jupiter on the right-hand side, and the other 3 planets on the left-hand side. All right, so I said around 7 o'clock, okay, again, Venus is pretty low in the sky, and we do have Mars and Saturn. And here, I have this one, okay, so this is what, 8 o'clock. Of course, the moon is going to be up. I think I'm going to be out there tomorrow for Glen Lee and do some testing on the equipment, because I got some equipment I have to test out. So, but here's my big discovery. I was playing around. We have an asteroid, Pallas. Apparently, its magnitude is 8.9. It was observed on October the 7th to be. You can't see this actually through a small telescope or binoculars, which is pretty shocking. I mean, you can see that. I haven't seen it personally myself, so I really don't know how it's going to turn out. Probably like a star. I don't think we have any real features to see. All right, so that was around. I said 9 p.m. Of course, we still have the full moon. Now, I came across another asteroid. Vesta, I think it's called, right? The magnitude is 7.35, as you can tell, but this is roughly 3 o'clock in the morning. But again, if this magnitude is right, and it's pretty bright, the one problem is locating it is going to be another tricky point, or a tricky task. All right, what do we have for celestial calendars? As you can tell, we have a meteor shower to happen. Of course, we got the full moon, but what's interesting with the full moon is that it's called the Hunter's moon, and some people are calling it a super moon. Or what's going to be unique about it is that it's going to be about 357,000 kilometers. It's going to cause some large tides on the following day, 17, 18, 19, 20. Of course, we have the Orion meteor shower. It's going to peak with 21, but fortunately, of course, we got the moon to compete with, so that's not going to really happen. And of course, I mentioned October 22nd, the last quarter. I did still put this in for the zodiacal lights. You know, it's pretty much done, but if you did get a chance to see it, great. I did see it in Arizona when Jay stopped by the side of the road for me, which is pretty nice. It's actually quite big. Okay, on October 30th, of course, we have the new moon. Now, one thing I kind of noticed, the distance of it. It's at 400, I did the math here, so roughly just under 50,000 kilometers in those 13 days it's going to travel. So that roughly works out to about 3,700 kilometers a day, which is pretty good. Okay, so November the 5th and November the 12th, we have the SN, or South Terran meteor shower, and the Terran North meteor shower that we have. I'll talk a little bit about it. Now, I have the faces of the moon here. You know, for me, it's kind of helpful for the new members to kind of plan around your observing. But I'm not going to start out until more like maybe around this time for deep sky imaging. All right, a little bit about zodiacal lights. You know, it's not much. It's pretty much over, but it's not going to happen to the spring, and it's going to happen towards the evening. So I'm not going to say much about it. You know, it's just the point of the matter is, it's very tricky to see if you have the moon, or it's cloudy, or it's hazy. You're not going to have a good chance of seeing it. All right, now, this is the meteor shower I'm going to mention is pretty much over. Okay, the Orion meteor shower here. Now, one interesting thing is this, well, again, of course, we have the moon to compete with, so it's not going to be much observing, but right in this chart here, it kind of gives you the time and where to look at and what directions to see it. But fortunately, I don't think we're going to be able to see it. And of course, what's nice thing about it is it's the debris that was left over from Halley's Comet. Again, this is what you were to look for. It's going to be right about here. Okay, now the S or the south meteor shower here. There's also the north and south. I don't know if you can see it. There's the south, there's the north. So there's Taurus, the constellation there. Now this is supposed to be the comet, or the comet here. Now they also believe that it might be a debris left over from a previous comet. But that's speculations, I believe. Of course, we have, now what's interesting about this, it's only going to be about 5. Some people say about 7 meters per hour. But what's going to be interesting about it is that apparently, well, every 2 hours we're going to have some really exceptionally bright meteors or fireballs, as some people might think about it. So, and we don't really have the moon to compete with, since it's going to be the beginning of the month. But, so there's, oh, I got to do something about this. Okay, there's Taurus, the constellation right there. There's Orion. I said roughly it's about 3 o'clock in the morning, so it's usually going to happen in the early morning of November the 5th. All right. Oh, that's it. All right. Thanks.
Also worth noting, the Leonid meteor shower is just one of the better ones of the year. Will come shortly after this time frame we've just shown you. So anyway, Chris has a few words to say before we break for our break.
Okay, so we're always concerned about our dark adaptation and what light we're using. So, last weekend I went to actually Princess Albert and I picked up this flashlight. It's a red flashlight. It's quite bright. What I noticed also, that when I'm using my headlight red, it's not always as focused on it, and it's kind of disperses the light everywhere. This flashlight is very focused. Something like this. And it's very bright, so don't try it into your eyes, because it's really bright. But I found it, I tested it kind of at home and a little bit outside, how much I can see with this, and it's really nice. $15, and I checked the flyer this afternoon. It's 30% off, so it's at $10 right now at Princess Albert. Right? Princess Albert.
The astronomer's store.
So you can try it, it's new, and you can come and see it. I'm going to leave it here, so you can also test it and see how it is. Thanks.
Okay, we're going to break for coffee and some goodies right now. Then they'll be outside of the room in the hallway. I'd also like to point out that Dr. Ben Sevlovic is here. He likes to look at chemical and atomic evolution. He helped discover a couple of moons on a few of the planets. Just to bring it down to earth a little bit. He has a BA in art science, McMaster, and MSc at the London School of Economics, where his thesis was on the interpretation of quantum mechanics. I needed you 35 years ago. He has a PhD from Dartmouth College in 2011 on the properties of supernova ejectors. He has 77 publications, a substantial number, his first and second author, with publications in Science and Nature, which are the creme de la creme in scientific publications. His toys, HST. Chandra, the 6.5 meter MMT, which isn't an MMT anymore, but still has that name. Nevertheless, a 6.5 meter telescope. Here we have a 0.25 meter telescope. The 8.1 meter Gemini, both north and south, Hawaii and Chile. And the Jansky DLA, very large array. Many of us have visited. He's currently working on the manufacture of 4 narrowband filters that are going to go onto the Magellan telescope, that's a 6.5 meter telescope in Chile. More than all of this, he used to be a member of the Hamilton RASC. So in those moons, he helped in the discovery of 3 moons of Uranus and 4 of Neptune. Tonight he's going to talk to us about exploding stars. And welcome to Winnipeg, and thank you very much for coming. All right.
All right, I feel like a pop star here. I got a microphone on, it's got my voice hot. Oh, wait, hold on. Well, as I get this going, thank you for that introduction. Wow, makes me feel very welcome here. Thank you for bringing up that I was a RASC member not too long ago. So it feels very rewarding having sat in the audience and having been to many talks as a child and going into high school, and now I get to be on the other end. And I've told people that I like to think of myself as a reporter of the universe. So I go out, I seek, I find stories, and I tell. And so now I get to tell with a kind of family that I've had for a long time. A family I never met here in Winnipeg, nonetheless, but one that has been very accommodating and inviting. So today's topic, exploding stars. These are among the most energetic phenomena in the universe. I will try to achieve some level of that energy with my presentation to explain to you about why I think that these are important, why everybody should know just a little bit about what goes on in the universe. This explosive phenomenon that has been so crucial for our existence. I'm going to start with kind of first order principles. This is the observable that tells us that we know what we're doing. And the basis of the fact, and this is a local story, is that we have watched stars explode. It had been theorized for many decades, in part by this scientist named Fritz Zwicky. I don't know if it's come up. He's an eccentric character. You can read many stories about him. This eccentric character, along with his mild-mannered observer, Walter Vaught, together came up with the idea of stars that would collapse and release a tremendous amount of energy. And something that were much more luminous than novae, they were supernovae. That term caught on. Well, this had been thought about, and we saw extragalactic examples for some time, but, you know, we never had an opportunity to see the star before. Well, then this happened. This is Sanduliac 969202. It's a blue supergiant with a large Magellanic Cloud. Now, if I showed you this without the arrow, it wouldn't stick out too much. It's not the brightest star. You can see others in the view. Right? But that arrow tells you something's going to happen. That's what happened. In 1987, there was a supernova explosion at that location. And the naming goes is that, so it's the year, and then the order that it happens with A, B, C, D, etc. And this is the first supernova of the year, so it's 1987A. Now, not only was it the first supernova, but it was discovered by a Canadian, Ian Shelton, who actually went to the University of Manitoba. And it's appropriate because, well, it's 1987, 8? Right? So there's a Canadian... so here was, well, let's say this happened, but even more importantly, going back to the scene of the crime many years later, and now it's been almost 30 years, if you do a high-resolution image of that region, now you can do with the Hubble Space Telescope, the star is gone. And in its place is a debris cloud, the debris left over by the star explosion. Now this is it's not a simple just debris field, but it's got these patterns to it, and one could spend a whole lecture, in fact we've been spending 30 years trying to understand this geometry. And we can go into the details at a different point, but right now I just want you to notice that the star is no longer there. So we had, when we say a pre-explosion image, this shows the star before that. So you have a star, you have an explosion, and then you have the remaining debris. And it's this debris that expands and seeds interstellar space with the raw materials that's needed for new stars. The star is gone. And that's kind of one of the takeaway points of the talk today. Why is this important? Well, with every explosion, you have the raw materials needed to create other solar systems. Right? This goes into forming new stars that have planets around. And these planets may have life, as it happened here on Earth. So I think it's terribly important to understand the fundamental process that goes on in the universe. Our livelihoods, our existence is dependent on it. All the materials, basically, beyond hydrogen and helium, were created in these massive star explosions. So, the iron in our blood, calcium in our bones, the oxygen that we breathe. Love that oxygen. This is all manufactured in these titanic explosions of supernovas. Okay, there is a lot to cover with supernovae, and I can't cover all the grounds, but I will guide us through a good portion of it. And two of the questions that I find most important and most interesting is understanding what are the types of stars that give way to supernova explosions. You know, for instance, I'll say right off the bat that a star, and this is actually a good disclaimer for everybody, is that the sun will not supernova, okay? There's a certain mass threshold that a star needs to achieve for the process of a supernova to take place. So beyond mass, are there other things that are more likely to give way to a supernova explosion? What are their progenitor systems? That's the terminology that I'll be using. The other question is, how do stars explode? This will involve some physics, but I'll hold everybody's hands, including mine, on what we think may be going on to bring these supernovae about. Oh, I have audio. Is it possible to do audio here? Can I plug in easily, or is it going to be complicated? Now, I'm amongst friends here that are familiar with relative scales of astronomy. But even for me, I think this video is cool and informative to understand just how big these stars are, and to give us perspective on how enormous. Now we're good. Yes. There's the moon, there's Mercury, and it has this cool music that's running. There's Mars. already see that the sun is pretty small, but we're just getting bigger. That one, there's Rigel, giant, we're going to go even bigger. There's the Thistle Star. It's getting even bigger now. Canis Majoris, one of the largest stars. They say largest. No, one of the largest stars. And then the fun part here is along the horizon of the star, and there's the Okay, now, supernova explosion, right? Don't want to be that close by when this thing blows. Okay. That gives you just a general sense of the sizes of the stars that we're dealing with. Size equates with mass, and mass equates with light. Let's look at this. So this is in terms of solar masses, which means the sun. And one solar mass, the lifetime of our sun is approximately 10 billion years. Given that the Earth is about 5 billion, made around the same time, there's still another 5 billion years for the sun's lifetime. Now, if you go in the opposite direction, you can see that a tenth of a solar mass star lives beyond the age of the universe. These things just keep going and going. But if you go in the increasing trend, you can see that the time in lifetime, in years, starts to shorten considerably. So once you get to a 10 solar mass star, you can see that the lifetime is dramatically smaller. This is only 30 million, right, as opposed to the 10 billion years. A star's lifetime depends mostly on its initial mass. And that initial mass will dictate the final fate of that star. So stars like the sun, low to average mass, will go through a period until there's a red giant, red supergiant, and form a white dwarf. A larger star will pass through and form a neutron star. This is where the supernova explosion mass threshold begins. We'll talk about this core collapse process. And then very massive stars, although there are details to talk, but generally the larger stars will go through the process and collapse completely in on itself to form a black hole. These are really exotic phenomena, and yes, I can put a little bit of a picture and some descriptive text, but it's hard to fathom what these things are. So I put some numbers here for you. All right? This is the object, and this is the density. And this is what 1 teaspoon at that density would weigh. And one grasp to find something analogous. So in the case of 5 tons, that's about an elephant. So if you had a teaspoon of white dwarf material, maybe if you're really strong, you could, well, no, it would be a real struggle, right? Okay. That's one. Now, the case of the neutron star is like the white dwarf, but you just kind of sat on it more and compressed it to the point that you have neutrons that are packed as tightly as possible together. And the density is orders of magnitude higher. And if you had a teaspoon of that, this is like 8 Empire State Buildings. So it's enormous. Imagine the gravitational field around that. Now we get around a black hole. Now, of course, we know nobody wants to be a teaspoon of that nearby because it can be ripped to shreds. So these two mark the final phase of the more massive stars. And the mass threshold is about 10 solar masses for which this core collapse supernova process happens. Here's a problem that happens often in astronomy in many fields, but it happens particularly because I want to study a process. I want to study a process that only happens in the most smallest, of minutest, of tiniest moments of a star's life. When you're talking about 10 million years, but you want to capture the seconds to minutes to days to which this core collapse process happens, that's a very small sliver of that star's life. Ideally, we want to watch a star from birth to death to understand the phenomenon, right? But stars live much longer than we do. And coupled with that, they're very far away. And this is problems in time and space. And let me digress just for a moment to give you a better understanding or appreciation of the difficulty. So I use as an example fruit fly. Now I hate fruit flies. I love bananas, and every time I get the bananas, the fruit flies come out at some point. I'm swatting away. But I was inspired one day looking at a fruit fly from one of my bananas. Because I thought of it like this. In the medical field, they love working with fruit flies to study genetics, okay? Because in a lab, a fruit fly's life is about 30 days. And if you look at our lifetime, which is about 30,000 days, we can go through many generations of fruit flies, see them from beginning to end, beginning to end, beginning to end, and characterize their entire life pretty easily, right? Now pretend that you're the fruit fly trying to understand a human, right? You're not going to live the whole time of a human lifetime. So how do you do that? So this is now the problem that we have. Us as humans living approximately 30,000 days, and then stars that are living 3 billion days. And the problem is actually exacerbated. It's even more difficult to be able to do that. So how do you do it? What you would do is try to get together as many people as possible. You would try to do a cross-section. You would work out the statistics. And you would see, all right, maybe you could start to work out things like there's male and female, and maybe you could begin to do this understanding that there's smaller people and larger people, and maybe they evolve from the lower to the taller people, but you have naturally different sized people. There's pregnant people, there's ethnicities, right? There's a lot of complications. So how do you get around that? You try to go to more people, right? And the larger sample size you have, the more statistics you can make about the population that you're studying. Okay. This is what we do with super. We originally started with 1 or 2 or 3 or 4 per year. And in the case of 1987, that reached the Earth, oh geez, I didn't say the date, February 23rd. Now, of course, the explosion had taken place about 200,000 years earlier because it took place in the Large Magellanic Cloud. But that February 23rd, today, there would have already been well over 200, 300, 400 supernovae already discovered. Right? Our rate of accumulation is much faster. So, wait, did you hear that? There's a supernova going off about once every second in the universe. And it works out approximately to 1 per galaxy per century. Now, obviously, you can't see all the supernovae, so many are distant that you can't. But approximately, 1 goes off every second. And so what one tries to do is to catalog them, and to look at the variety, and to study them in different filters, and to get spectroscopic information. The supernovae are very influential, not only in the sense of manufacturing the heavy elements that I was talking about, but there have been cases where the stars have exploded in our own galaxy, and people have witnessed this. And it really is an amazing thing to have been around at these times. Here is a great engraving of Tycho Brahe observing a supernova in 1572. This is now known as, we see this today as Tycho supernova. You know, the light would be so bright that you could see the star during the day. And in the case of the RASC supernova, apparently you could read at night as well. Brighter than the full moon. You can imagine the peoples of around 1000 AD. How would they comprehend what they were seeing? Finding supernovae. So how do we do it today? It's basically a matter of imaging the field, returning to it, and looking for a difference. In discussion today, we were talking about one of the pioneers, one of the amateur pioneers, who did this before there was imaging capability, and he would discover it by eye. This is Reverend Robert Evans, this Australian, I believe, individual. His memory was so good that he would do it visually by memory. He would look in the telescope and look through all the galaxies that he would want to pan that night, and would not have to look at a reference image of that galaxy. He could tell whether or not a supernova had gone off. And he was able to do this for 46, but something in the 40s of visually confirmed supernova. Nowadays, however, there's very sophisticated all-sky surveys that do this routinely with CCD technologies, able to go to very faint limiting magnitudes. And while there are these groups, there's very good, we call them amateurs, but I think it's just a different way of saying astronomers who have day jobs, right? In this case, this is Stu Parker, who runs a dairy farm by day. And he's fantastic. You know, he has a dairy farm of several hundred cows, and he has a name for every individual cow. And he told me something, another amazing thing. Did you know that the average lifespan of a cow on his farm is 17 years, compared to most American farms where they're no more than 3 or 4 years? I don't know. There's some trivia for you. Okay. Anyhow, I work with Stu a lot, who has spent, instead of buying a nice Mercedes, you know, he's bought really good telescope equipment to be able to do this. And he has about 3 telescopes as part of his observatory. He does routinely look up. He does the imaging fields, and then does the data processing and blinks by eye to see if there's a new supernova. Here's a test. Can you see where the supernova is? By eye. It's developing in these series of images. There it is there. So again, it's this idea of here's your template image, and then returning it. And then these days, what you do is an image subtraction. You take this image, you subtract that from it, and you should, in essence, only have that one source. Here, an image actually taken by a student. And this I like because it looks old school photograph. So there's this kind of little fuzzball in the distance, and then please appreciate that that is an entire galaxy of stars, right? Say of order 100 billion stars. And then all of a sudden, one of those stars is that star, which starts to compete with the entire galaxy. That's a tremendous energy output. And in some cases, if you have a less massive galaxy, a dwarf galaxy, the supernova explosion can actually be even brighter than the entire galaxy. So I talked about these surveys to discover supernovas. So I've been doing this for many years. I don't do it as much these days, but I did it for a long time. And we have to react quickly to this, because some of the most important information about a supernova, namely properties of the star that exploded, are best observed in the early phases, in the first hours to days after the explosion. So we have to rush to the scene, and through text messaging and emails, I work with a team of people to coordinate facilities around the world and in space to observe these as quickly as possible and as thoroughly. So whether you're doing an ultra marathon, you're out in the woods, you're rocking out on your guitar, you're climbing a glacier, we'll respond. Okay. What types of stars explode? Over the years, we've seen incredible diversity in the explosions, which is to say they aren't all the same. And they change in the amount of the luminosity that they output, as far as peak luminosity, and the evolution of the light. Some rise and fall more quickly than others. We also see differences in the spectroscopic qualities, the elements that they are most strongly associated with. And we take this to mean that the stars themselves that are exploding are different. But how can we connect which explosions are associated with which types of stars? It comes with the spectrum. And I won't belabor the point, but I just want to put out there that we have a classification scheme for supernovae, and it's based on spectrum, which I'm not showing, but we can potentially go into that later. They're broadly defined by whether or not they show hydrogen. Now, what are most stars? Big balls of hydrogen, burning hydrogen, right? So a large portion of supernova explosions are these, type 2. But a good fraction don't show conspicuous hydrogen as their optical spectrum. These are the type 1s. Now, as the data improved, this was originally in the 1940s of when this classification started. As the data improved, we saw that this type 1 had a bifurcation. And this is important because there's a fundamental difference between these two progenitor systems. In the one case, we have what are called type 1As, and these are rich in silicon and sulfur. These occur in both elliptical galaxies, associated with older stars, and spiral galaxies, younger stars. We now take this to be the progenitor system associated with white dwarfs. We'll talk about those stars. Most of what I'm talking today is going to be not white dwarfs, but on the other hand. But this is an important type of supernova in that they are standardizable distance ladders. And people won the Nobel Prize in using this type of supernova in measuring the accelerating expansion of the universe. But on the other side, we have the core class, massive stars. And these are only found in spiral galaxies. And in this interesting case, the type 1Bs and 1Cs, 1B is associated with lithium, type 1C is not. They're silver. These stars have somehow been stripped of their hydrogen output. There are various mechanisms by which that happens. One is the star's winds that can blow off the material itself. The other is interaction with another star on top. Type 1A scenario. So this is where we have a white dwarf. And this is actually a star like the sun, evolved, gone through various processes, and ended up as a white dwarf. Has a nearby companion that's pooling material onto it. And once it reaches a certain mass calculated by Chandrasekhar, so we call it the Chandrasekhar mass, it undergoes a runaway thermonuclear explosion. This is one of the scenarios that we do. However, kind of cutting-edge science is pointing towards an alternative scenario where you have two white dwarfs, stars, that are coming together, reaching that threshold mass, potentially, and then exploding as a supernova. So this is the double white dwarfs. So that was the type 1A. Now we're talking about the type 1B's and the type 2's. Here is kind of the easiest interpretation for us, is that a single star evolves and undergoes core collapse through a process that I'm going to discuss. And most of these single star evolutions tend to evolve into red supergiants, but not always. I showed earlier 1987A said in the San Juliac star, that's actually a blue supergiant. This is where a lot of work is happening these days in understanding binary systems, because actually most massive stars don't grow up alone. They have some kind of companion that formed at the same time. And the majority of those companions will swap material. Now here's a nice animation showing how two stars throw material back and forth. And the star that was originally more massive pulled its material onto another and is evolving more quickly. And I think right around now it's going to go. Wait. There's the supernova. And there's the masses here. And this star, which is about 30 solar masses, is going to undergo an explosion. And there it now. It pulls off a lot of material, evolves into a red supergiant, and then there's the explosion. We're increasingly facing these types of scenarios because we have observational evidence supporting the notion of stars that are coming into close proximity. This was a great press release by this team. They had evidence that two stars were so close, they called them the kissing stars, because there was a close interaction between the two. Now, if you put me under the spotlight, do I really believe this is happening? No. But hey, it makes for a great press release. Okay. So I talked about stars exploding. Well, what is going on? How can we actually understand what is going on? A star starts off as basically a lot of hydrogen with some helium. At the core, there's nuclear fusion. So unlike nuclear reactors that we have that work on fission, which split atoms, okay, this is fusion. This is bringing atoms together. And that process of bringing atoms together can release energy, a lot of energy. It starts off with hydrogen in the core, and then when it exhausts hydrogen, it goes to helium. And then it goes towards carbon. And this process continues until you reach iron. Now once you start binding iron together, it no longer releases energy, it's endothermic, it absorbs energy. And you have gravity wanting to pull in all the star towards the center. And normally it's the radiative pressure that pushes out against this, that keeps the star stable. This is balance between the two. But without this radiative pressure, a collapse ensues. Now the collapse ensues until you reach a certain point at which the atoms don't want to go any closer together. I'll say this. So originally you had a proton-rich material, and through captures of electrons, so those protons become neutrons in that way, and there's photodisintegration. These photons going with these gamma rays going and splitting the protons into neutrons. That's what forms all the neutrons. They collapse, they can't get any closer, and then there's this rebound shock. And it was thought that this rebound shock is enough to disrupt the star. There's a lot of details in this. And I was at the University of Manitoba today talking about how this cartoon notion of this implosion, explosion has a lot of uncertainty. And there's actually incredible physics to be acquired here through the next generation of multi-wavelength facilities. So how do we investigate supernova explosions? One way is to do a bomb squad investigation. This is what some of my research really tries to exploit. So there's some crime scene, there's a bomb that has gone off, you go and investigate it. One of the first things you're going to do is, as you enter the room, is you look around and you see where the debris is. Did it go in all directions equally, or was it preferentially in some directions? This is the same thing here. This is the remnant of an explosion that happened about 330 years ago. It's supernova remnant Cassiopeia. This is a Hubble Space Telescope image. The color coded such that red is sensitive to sulfur material, the green is oxygen-rich material, and this dappling purple-blue is hydrogen and nitrogen-rich. When one looks at this, you have to see that this is the stellar debris that's been thrown out in various directions, but not haphazardly. There's structure to it. There is coherent structure. And I'm attempting to understand how that structure reflects the explosion dynamics of the corridors. And a lot of my work goes into developing three-dimensional reconstructions of that debris field. Here, this is the reconstruction rotating about. It's color-coded by Doppler velocity, so blue is blue-shifted, material moving towards us. And in the back is red, or red-shifted, stuff moving away from us. And there's these large rings throughout the remnant and these interior cavities. And all this gives us information about how that explosion proceeded. There is some fun press that was associated with this paper, and it's very descriptive, kind of radioactive bubbles made punched holes in supernova's heart. And the idea is that the explosion was so turbulent inside that normally the heavier material, which we would think would stay at lower velocities, it's a conservation of momentum. So P equals mv, mass times velocity. Heavier mass would mean less velocity. But because there's such turbulence in the explosion, it allows the nickel-rich material, the heavier element, to actually move out ahead. And here, this is a simulation, by the way. This is seconds after explosion, and this is hours. You can see how the nickel-rich material in blue has raced out ahead of the lighter elements, the oxygen and the carbon. So if you look to Cas A, and in this case it's the iron that we see in X-ray wavelengths, and I've shown in red the 3D reconstruction made from optical to near infrared. There's an interesting coincidence between where we see iron-rich material, which traces the nickel-rich, because the nickel decays to cobalt, decays to iron, and the large rings that we see in Cas A. So the takeaway here is that by looking at the remains of an exploded star, we can get insight into how that explosion proceeded. Okay. This is kind of the last bit of the talk where I want to focus on what's really new and exciting now. What I showed you earlier was new and exciting, but this is encompassing some of the latest trends in the research. And this is namely that stars are doing things before they explode. Now, when I sat in that audience, I was taught that the core activity was detached from the star's on. There is such a density gradient between the two that whatever, the envelope won't ever know what's happening with the core. And yet, there are instances where there is a supernova that has had precursor activity associated with it. Now let me explain what I'm showing on this graph. This is a supernova called 2009 IP, and it's a stupid name because the supernova actually happened in 2012. But what happened? What happened? In 2009, they had a detection. Somebody took an image of a field, they compared it to something that happened beforehand, an image that was taken beforehand. They said, hey, we got a brightening happening here, give it a name, supernova 2009. However, as they continued to monitor it, it didn't reach the luminosity for a supernova. Right? It was something that's called a supernova blast. And this energy scale is something that we've seen in other stars in giant eruptions. Maybe some of you have heard the system Car, like this. So this is a star that kind of, in one episode in the 1800s, it just kind of fluffed off 10 solar masses of material. It went from being a star that was hardly visible to the second brightest star in the sky. So this system underwent some kind of eruption, and then it kind of was quiet. Something happened, and then in 2011, whoa, back and forth. up until this point here where there's this double peak, this precursor and then the actual supernova. This is remarkable, right? The star is signaling its death through this precursor activity. And in fact, it's so exciting for us because this makes it possible to predict if a supernova explosion is going to happen. Remember I talked about how difficult it is in studying a star's life because they live so much longer than we do. And so capturing those final moments, knowing when that's going to happen, seemed to be impossible. And yet, here is a case where the star was letting us know. It's kind of, if you know somebody's going to be sick, it's like, oh, get them to the bathroom, right? So this is the case of like, oh my gosh, this star's going to explode. Get the telescopes out, right? This is a very exciting frontier for us. So what's interesting that if a star is undergoing an eruption, and this is an extreme case, so characterizing how prevalent this is amongst all the various stars is not trivial to do. But if this is the case of what's happening, if there's a synchronization between this precursor activity and the actual supernova explosion, it may be that this idea of the onion skin interior of the star is wrong. If you have the core activity connecting with this eruptive precursor activity, something is going on. So instead of this, it must be much more turbulent. And this is going to be a key idea as we move forward in understanding how the stars explode. So there's an intimate relationship. Let me say this. There's an intimate relationship between the star, what type of star it is, its interior structure, and the actual explosion mechanism. So, moving on to now future frontiers. There's a project called the Large Synoptic Survey Telescope. I'm guessing it's been brought up. It's a project that's been in development for a long time, a lot of money thrown at it, and it's to be coming online in the next couple of years. This survey will be covering the visible sky every, say, 4 nights to a limiting magnitude of 24 with single exposures lasting 15 seconds. They're taking 15-second exposures over 20 seconds. And once they stacked it, it's going to go down to a limiting magnitude of 27 meg. And they're going to be able to span that gap, that luminosity gap between the actual supernova and the precursor activity. And I throw here, it's going to be a real tsunami of information because they claim they're going to be potentially finding 100,000 supernovae per year. That's a lot. And along with this discovery machine, we're going to have new machines to be able to follow them up. And here's an image of the giant Magellan telescope, which the Harvard-Smithsonian is a key member. And here, for perspective, is the person. And they intend for this to be operational in my lifetime. I hope so. But I see some youngsters in the audience. It might be your kind of toy to use within the future. This is a hilarious slide because this was supposed to be future research in, someday. Well, the future is now because we have gravitational waves. And I'm sure that news is spread here. And this is very exciting for the field because I talked about this core activity and the idea of crushing that star down to neutron-rich material and all this turbulent flows and trying to understand how this encourages the supernova to take place. Well, gravitational waves are actually emitted by this core collapse process. And binary black hole mergers are old news. We discovered that. The next big project is to try and detect gravitational waves from the collapse of a massive star. And these are just animations for this thing. But yeah, so the gravitational waves were detected by these merging binary black holes. Basically, you have this shift in space-time, and if the asymmetry of the supernova explosion is great enough, it will produce the gravitational wave signature. And depending on how that asymmetry is brought about, this tells us about, this produces different gravitational wave signatures that we'll be able to determine. So finally, we saw some nice sky images. I'll tell you that during the winter months, when you look up at Orion and you have a look at Betelgeuse, you're reminded that that's a red supergiant. That's a supernova candidate. And maybe not today, and maybe 10,000 years from now, that thing will explode. But thankfully, at a safe distance for us to reach. Thank you very much.
Do we have any questions?
Good. Most of it seems to be being done, what you were talking here, in our visual spectrum. Is there what kind of evidence is coming out of different spectrum?
Great question. So you're asking about my work. I'm a specialist in ultraviolet, optical, infrared. And this is a lot of the work that I've shown here. But clearly there's across the spectrum, so X-ray and radio. Each of those wavelengths are sensitive to different aspects of the supernova. In the extragalactic cases, the X-rays produced in the supernova are too weak to be detected. However, the interaction of the supernova blast wave with surrounding material produces X-ray and radio emission. So when I talked about working with people to coordinate facilities, we do radio and X-ray to understand the mass loss environments. So as the mass waves pushing out against across the material left by that progenitor star system, it's telling us about what kind of evolutionary state that star was in. And in fact, it gives us information about that precursor activity, because there can be spikes in the radio and X-ray emission that's associated with as the star comes to some kind of sudden jump in density associated with an eruption of the star some number of years ago.
You mentioned 1572 there was a visible supernova, but this is still maybe 10,000 years ahead before this might. So it's not, there's nothing soon. It's like in hundreds of years time frame. There's no candidates closer like that one. Must have been very rare.
Well, again, so I painted an exciting picture, and it is that we can predict supernova explosion. But for the most part, it's an unpredictable phenomenon. And if I put my money on it, perhaps Betelgeuse would not be the first one that I'd be waiting around for. I haven't done the exercise of going through the star catalogs and seeing which would be the most likely one I'd want to follow. But generally, no stars. I did do the exercise of, are there any massive stars that we would need to be afraid of in a mass extinction? Thankfully, that's not the case. Yes?
You were talking about type 1A supernova, and you mentioned briefly, so I guess a little bit out of but you mentioned briefly that you were looking at double white dwarf stars.
That's one of the progenitor scenarios for type 1A supernova, correct?
So does that have any potential impact on our distance estimates? Because we use type 1A supernova to determine distances to galaxies and whatnot, right?
The standard approach, the standard answer to your question is they feel comfortable, I think I do as well, using supernovae without understanding the progenitor system, which is to say, if you don't know, if you just act as it being a black box, the properties of these certain class of explosions in type 1As are so reproducible that you don't care what's happening on the inside. You just kind of look away at those fine details, because it's shown time and time again that there's a way you're able to do this is there's a relationship between the peak brightness and the length of the light curve. And they can scale it to find out if you have a length of light curve, you can figure out what the peak brightness is going to be. It's awesome. But nobody knows for sure if the progenitor system can affect that relationship. And the extrapolations made for the idea of accelerating expansion of the universe is largely based on the few points at the most distant supernovae observed. And who's to say that those few points where there's a lot of error and scatter aren't from some kind of difference in the progenitor system that may not completely follow the relationship that we use at lower dimensions. So your question is a very good one. Does the progenitor system affect the relationship that they use to calibrate the distance lag? That's another question. But I don't want to leave you like, I don't believe it. Well, it's something to be.
More questions? Well.
Thank you very much for coming and talking to us.
Thank you for having this wonderful